In the previous video, we talked about activations, but we never said what information we actually need to keep for an activation. That's the topic of this video. An activation record is all the information that's needed to manage the execution of one procedure activation. And often this is also called a frame. That means exactly the same thing as activation record. These are just two names for the same thing. Now, one interesting fact about procedure activations is that they have more information in them than you might expect. So in particular, when a procedure F calls a procedure G, the activation record for G will actually have information not only about G, but very frequently also about the calling function F. So typically the activation record for a procedure will contain a mixture of information both about that procedure and about the procedure that called it. Now, up to this point, we haven't said why we need to keep information about activations at all. And the reason is that there is some state associated with each procedure activation that is needed in order to properly execute the procedure, and we have to track that somewhere. And that's what the activation record is going to be for. It's going to be to hold the information needed to properly execute the procedure. So let's look at that in a little bit more detail. Let's consider the situation where procedure F calls procedure G, and what is going to happen. So conceptually, what happens when F calls G is that F is suspended. F is going to stop executing while G is running. So G is going to be using the processor and all the resources of the machine. But when G completes, we want to start executing F again. F is going to resume. And so in between, while G is running, we have to save the state of the procedure activation of F somewhere so that we can resume it properly. And that's again what the activation record is for. And so G's activation record is going to have information in it that will help us to complete the execution of G. So there'll be some information about G that we just need in order to run G, but also G's activation record is going to have to store whatever we need to be able to resume the execution of procedure F. So let's work through an example. Here's one of the programs that we looked at in the last video, and here is a design for a concrete activation record for the procedure F. So we'll have one position for the result of F that will hold the return value after we've finished execution of F. There'll be a position here for the argument to F. So F only takes one parameter, so only need one word here to hold the argument to the function. There'll be a control link, so a pointer to the previous or the caller's activation. And we'll also have a slot for the return address, so the address in memory or the address of the instruction that we are supposed to jump to after the execution of F completes. So now let's just execute this program by hand and work out what the activation records will look like on the stack. So when the program is first invoked, it will call main. There will be an activation record for main. Okay, but we're not going to worry about that. We're just going to focus on F. So there's some stuff for main, but we're not going to talk about that. And then main is going to call F. All right, and so when main calls F, an activation record will be pushed onto the stack. We'll have four slots in it, or four fields for values. And what will go in those? Well, the first slot is for the result. Well, it's just starting to run. F is just beginning execution, so there's nothing to put there at the moment. That gets filled in when F returns. The second position will hold the argument to F, so that'll be the number 3. The third slot will hold the control link, so that's going to point back to the activation for main. And the fourth position will hold the return address. And this is actually not completely trivial because F is called in multiple places. So if you look at the program, there's a call to F in main, and there's a call to F inside of F itself. And so depending on where the function is called from, after that function completes, we want to return to a different address. In the case of main, when this call to F completes, we want to return to the whatever instruction comes after the call to F, which is just going to be something that wraps up the execution of the program since it's the exit point of main. Inside of F, it's going to be the conclusion of the conditional. So this point double star here is going to be whatever is left of the conditional and then the return from F. So depending on where F is called from, we want to return to one of two different places. Okay, so in this case, F is being called from main, and so we'll put the single star address in that position of the activation record. All right, so then F is called a second time. The body of F executes, the argument 3 is not 0, and so we wind up calling F again. What that means is that another activation record will be pushed onto the stack. This will also have 4 slots. It's an activation record for F. I probably should label these. So that's an activation of F. This is also an activation of F. And what goes in this one? Well, again, the result doesn't have anything initially in it. The argument in this case would be 2. The control link in this case will point back to the previous activation of F, and the return address in this case will be the point double star. All right, and so after 2 calls to F, this is what the stack will look like with this particular activation record design. So here's the same picture, just drawn a bit more neatly. There's one additional thing I'd like to point out, which is that this stack of activation records, and let me delineate the activation records here, is not as abstract as the kinds of stacks you were probably taught about in a data structures class, if you've had such a class. So here, there are distinct activation records on the stack, and we treat them as such, and the runtime system will treat them as such. But this is also like one gigantic array. All of this data is just laid out in contiguous memory. These are all contiguous addresses, and one activation record here just follows on to the next address immediately after the previous activation record. And compiler writers will often play tricks to exploit the fact that these activations are adjacent to each other in memory. And we'll see one such potential trick in just a moment. To summarize some of the highlights of this example so far, I want to repeat that main is not very interesting. So it has no argument or local variables, and its result is never used. And so while it does have an activation record, we're just not focusing on that, and we're not concerning ourselves with what goes in that activation record. We're just focusing on the activation record for F. Just to be sure this is clear, the star and double star that I used in the example, these are addresses in memory. These are actual memory addresses, and they refer to addresses of code. Those are the addresses of the instructions that come after the call to F, so that's the place where F would return to. And finally, I want to stress that this really is only one of many possible activation record designs. You could design a different activation record for F that had different information in it that would work just fine depending on the structure of the rest of the code generator and the runtime system. So in particular, many compilers don't use a control link because they don't need an explicit link to be able to find the calling, the activation record of the calling procedure. And in fact, in your class project, the Cool compiler, you won't be using a control link. Most activation records won't have the return value in the activation record because it'd be more efficient and convenient to return it in a register. All right, so this is just one possible design, and it would, and you could design other activation records that would work just fine. The important point about an activation record is that it just has to have sufficient information in it to enable the generated code to properly execute the procedure that's being called, and also to resume execution of the calling procedure. So far, we've only looked at the procedure call for this activation record. We haven't talked about what happens when activations return. So let's consider what happens in our example after the second call to F, that's this one, this activation down here, returns. So what's going to happen is we're going to make the caller the current activation. This will actually become the top of the stack. So I've got this big fat green arrow here to indicate that this is now the current activation, this one up here. Okay, so this is the call, this is the what was the caller, and it's now going to resume executing. And the interesting thing here is to note that, like as I said before, this isn't as abstract as a stack in a data structures course. So while we have restored this as the active procedure, this data down here, this activation that was running is still there in memory. And in fact, we can go and look at it if we want to. And the way I set this example up, in fact, we need to, because the result of the procedure that we called is now stored here in the first word of this activation. All right, so when F begins executing again, it's going to have to look up that result in order to know what the result was of the procedure that was called. So the advantage of placing the return value in the first position in the frame is that the caller can find it at a fixed offset from its own frame. Let's back up and just see that. So here, when the second call to F has returned and the first call here has resumed executing, this call, the code for this call will know that the size of this activation record is 4. Okay, there are 4 words in this activation record. And so it can find the result of the procedure that it called in the 4+1 position, and 5 words past the top of the frame. So in particular, it'll be able to find this word in memory. And even though this has been popped off the stack, as I said before, that data is still there, at least until another procedure is called. And so if we immediately read the result of the function call after we return from the function, we'll be able to pick up that result and then use it in the continuation of the execution of the calling procedure. And once again, I just want to stress, I know I've said this a couple of times, but it's very important that there's absolutely nothing magic about this organization. We could rearrange the order of the elements in the frame. We could divide the responsibility between the caller and callee differently. And really the only metric here is that one organization is better than another if it results in faster code or in a simpler code generator. And I know I also mentioned this before, but it's also an important point. In a production compiler, we would put as much of the frame contents as possible in registers. And in particular, there'd be a special effort to pass the method result and the method arguments in registers because those are accessed so frequently. Finally, to sum up our discussion of activations and activation records, the issue is that the compiler has to determine at compile time, okay, so this happens statically, the layout of the activation record, and it also has to generate code that correctly accesses the locations in that activation record. And what does this mean? This means that the activation record layout and the code generator have to be designed together, okay? So you can't just design your code generator and then figure out later what your activation record layout is going to be, or vice versa. These two things need to be designed together because they depend on each other.